Okay, thank you. Let me just say I'm happy to be here and give this talk today. So first, let me just acknowledge my collaborators, which are um, listed down here. So as the title of this talk obviously indicates, I'm going to talk about kinetic turbulence in astrophysical plasmas, and in particular about waves and structures that we can find in this type of turbulence and how they might be related to each other or maybe not. So I'm going to start with waves. And in particular, in this talk, I'm going to focus on solar wind turbulence. Why? Because for the solar wind, we have by far the best measurements available. And two great examples are shown in these two plots. So we can send spacecraft out there and we can probe the plasma dynamics there in situ. So the wind flies past the spacecraft at speeds ranging from about 400 to 800 kilometers per second. And then we can measure the time trace of, let's say magnetic fields of some other quantity as the wind flows by. And by invoking the Taylor hypothesis, which was mentioned in the previous talk, we can convert the frequency in the spacecraft frame into an effective wavelength in the plasma frame. So some historic background first. So here on the left is a picture from a paper by Belcher and Davis from the 1970s, showing a direct detection of Alvin waves in the solar wind. So these are Alvin waves, for those of you who maybe don't know. These are probably like the most simple and most famous type of wave that you can have in a magnetized plasma. So they're supported by a mean magnetic field, and the waves travel up or down the mean magnetic field. As they travel up or down, the displacements are in the transverse direction. So you have fluid velocity and magnetic field perturbations. And these perturbations are either in phase or out of phase with each other, depending on the direction of propagation. And here on this plot, they plotted all the magnetic field components together with the velocity components, and we can see that they fit on top of each other, so they satisfy this relation. But there's also turbulence in the solar wind, and here is a much more recent paper showing this turbulence measured in situ with the spaceship. And you can see we have many, over many decades in scale, we have power spectra. But the solar wind, it's turbulent, but it's also very weakly collisional. So we have, here in this range, we have a fluid type of turbulence where the plasma behaves as a single conducting fluid. This is the so-called MHD inertial range with a Kolmogorov type magnetic spectrum. However, because it's so weakly collisional, at the near-Earth solar wind, the collisional mean free path is almost equal to the distance from Sun to Earth. So the fluctuations can actually cascade all the way down to the plasma kinetic scales. By kinetic scales, I mean scales comparable or smaller to the thermal ion gyro radius. So the radius of the gyration of the ions perpendicular to the magnetic field. And there the turbulence changes because the ions decouple from the electrons. And it's not just that. The turbulence becomes essentially kinetic in nature because there's also the turbulent energy can be dissipated, but it's not dissipated by collisions. It's dissipated by, it's channeled into the ion and electron internal energy via collisionless wave particle interactions. And the fraction of energy that goes into the ions and electrons, so the ions can take up a larger or smaller fraction of the energy than the electrons. And because collisions are so weak, there is no guarantee that these two temperatures will equilibrate. So it's essentially the problem of ion and electron heating is an interesting plasma physics problem, okay? So how do we combine these two aspects? Well, there's a very known conjecture which is appropriate for strong wave turbulence. So this is the case I'm going to consider in this talk by Goldreich and Streeter from 1995 for MHD, which says basically that the wave crossing time is up to order unity in balance with the nonlinear eddy turnover time. And this is a statement that is made scale by scale. And so this concept has been more recently also adopted in some kinetic scale models of turbulence. And this has, as I mentioned, some interesting implications for the ion electron heating. So this is the range that I want to focus on in this talk, right here. So this so much about waves. Now going to structures, quite generally in a variety of turbulent systems, almost any turbulence doesn't have to be a turbulent wave system, we see structures forming. And here in particular, I give two examples of structure formation in a turbulent wave system. So here on the left, we see some examples from rotating turbulence, for example. Here in the middle is a picture from one of my own kinetic simulations showing electron density fluctuations. And here this line shows the magnetic field lines. And here is here's an example of the entropy in stratified turbulence. So we have this localized intense structures forming. So then when we go back thinking about waves, maybe like we would think of some, when we think about waves, maybe we would think about some linearized set of equations of a more general nonlinear description from which we obtain the wave dynamics. So if we have this kind of localized structures with some high amplitude, is the linear wave dynamics at all relevant for these intense structures? And this is actually the question I'd like to address in my talk. Also, another aspect is, well, naively, one might think the eddy turnover time is inversely proportional to the fluctuation amplitude, and I'm explaining later why this is naively so. The nonlinear time, maybe it will be accelerated when we have locally some intense high amplitude events. So how does this go together with the wave dynamics? Can it keep up? And again, there's interesting implications for the ion and electron heating here, because let's say if there would be some wave properties preserved in the structures, maybe we could apply some like linear wave damping mechanism to study the heating in the structures. But if the structures are fundamentally different, then all this breaks down and all this is completely useless. So a few things about the methods that we use. So we combine 3D fully kinetic plasma simulations with spacecraft data from spacecraft observations. So I use a 3D kinetic plasma code, which is called OSIRIS. So basically we solve the charged particle dynamics, ions and electrons, self-consistently coupled with the Maxwell equations. So the particles serve as sources for the Maxwell equations, and everything is done self-consistent. These are massively parallel computer simulations. But in addition to that, I'm also going to be using data from spacecraft, in particular from so-called cluster and MMS mission. From cluster, we use data from the free-streaming solar wind, whereas from MMS, it's actually from the Earth's magnetosheet, which is actually not that of a clean type of turbulence. However, MMS has much better instruments on board, so you can measure certain things that you cannot measure with cluster, for instance. And so here's an example, for instance. So here's the data from some simulation that I'm going to be using. This is a driven 3D kinetic simulation. Here's an approach to steady state. And the spectrum, as you see, is not Kolmogorov, because as you've seen on the introductory slide, showing also data from solar wind measurements, in the kinetic range, the spectrum is much steeper because it's a different type of turbulence. And down here, I compared the scale-dependent flatness of different components of the magnetic field and of the electron density in the simulation, and also from the data from the spacecraft. And we can see that there's some intermittency here. So we have values above the 3, which will be expected for a normal distribution. So this is the data that we use. So now, coming back to my original question, I mean, maybe the question is kind of clear as on its own, but when you start thinking like, could we construct some kind of diagnostics to actually measure this, things become maybe a bit less obvious, and for the following reasons. So if we consider strong wave turbulence, the wave frequency, this is just a rewritten version of the critical balance statement, is comparable to the inverse lifetime of an eddy. And because this is the lifetime of the eddy, this also determines the uncertainty for the measurement. So basically, the uncertainty is of the order of the frequency. The uncertainty is the order of the frequency itself. So basically, there's no hope that we can measure any dispersion relation. So what is done instead in simulation and also in spacecraft observations is you can compute the power spectra of different quantities, for instance, different components of the B field or of the density field, and you can take ratios of these spectra. And from these ratios, once you have these ratios, you can take the linear predictions and you can directly compare the linear wave predictions with the measured ratios. So in this sense, you can probe if there's some signature of linear wave dynamics. However, this is also not quite what we'd like to do here, because we'd like to probe the rare extremal events. And once you do a Fourier spectrum, you lose any information of intermittency. So what we came up with is the concept of so-called generalized field ratios, which are similar to the original ratios, except we use, they're based on wavelet transform coefficients. So you can, with the wavelet transform, basically you can, they're sort of like bandpass filters in a very simplified way. So you can localize a signal simultaneously in real space and spectral space. So in that sense, you retain information about scale and variation in space. So in this sense, you can make these ratios sensitive to this kind of rare events. So this is what we did. And here are some of the results we obtained. So there's quite a few figures shown on this plot here, but let me just focus maybe on this middle row right here. So in this middle row, we consider the ratio of the electron density to the perpendicular magnetic field. And we construct two types of ratios. So for the first type, basically we have the scale filter fluctuations, and we compute different order moments of these fluctuations, the first, the second, third, fourth, fifth, sixth. So as we go to higher order moments, these ratios become progressively more sensitive to the more high intensity extreme events. And here on the right, you can also, what you can also do with wavelets, you can, if you have complex valued wavelets, you can compute sort of like a local power spectrum, point by point. And then you can take conditional averages of those spectra over regions where the spectral density is above some threshold C in some normalized units. So here we vary this threshold C on the right, and on the top we vary the order of the moments. So the red lines are the linear wave predictions for kinetic Alban waves. I think the pointer does not work. Anyway, so here's the linear predictions for kinetic Alban waves are the red lines, and the kinetic range that we're mostly interested in is in between those vertical dotted lines in the picture. So the first vertical dotted lines is the ion kinetic scale, and the ones on the right are the electron kinetic scales. So we're interested in this range of scales. And in this range of scales, we actually find that even if we kind of try to give a higher weight to these more extreme and rare events, actually the values of the measurements don't change that much. So actually within order unity, even those rare and intense events are in reasonable agreement with the linear wave predictions. So the structures themselves actually carry a wave character. So this is fine, but why would this happen? Well, so one argument is just the one I mentioned in the beginning, it's just critical balance. So these timescales must somehow balance, maybe perhaps even structure by structure, but it's maybe kind of a generic argument. So I try to think of if there's something maybe more specific that we can say about this in addition to the critical balance argument. And well, there is one thing that we can say. Let's look at some equations. So as I mentioned, the turbulence in the kinetic range is as the name says, it's inherently kinetic. So if you want to describe heating, you need a kinetic model. But aspects of it actually can be even described sometimes with reduced fluid models. And here's one example here on top of some kind of fluid model that's appropriate for this range. So psi is the so-called magnetic flux function, and then we have the electron density, and this is how the equations look like. So the nonlinear terms on the right are basically cross products between two perpendicular gradients. So perpendicular, I mean perpendicular to the mean magnetic field. And what's maybe interesting to observe is that, let's say, consider the case then that both of these fields, the electron density and psi, just depend on the parallel coordinate and just on the radial coordinate. Because they all depend just in the perpendicular direction on the radial component, all the gradients will be in the radial component, so these terms will cancel geometrically. Another case, if there's just dependence on one of the perpendicular coordinates, let's say x, all the gradients will be aligned and the nonlinearities will cancel geometrically. So then you're left with like a wave system. And interestingly, actually simulations and observations find structures that are actually either resemble like elongated sheets or circular tubes. Here's an example from a simulation on the right. So the idealized versions of these structures would be actually exact wave solutions because the nonlinearities cancel geometrically. Of course, in a turbulent system, you can never realize such ideal structures, so probably, there's going to be some misalignment, but still, on average, there's probably some cancellation of weakening of nonlinearity. And by the way, equations similar to this type can be also obtained for other systems in the strongly anisotropic limit, in particular for rotating turbulence or for just MHD turbulence. So while these are very simple equations, can we actually find any evidence of this sort of thing in our data? So I went back to our data and I considered just the nonlinear term in the first equation. So this term can actually be rewritten as a cross product of the perpendicular electron fluid velocity and perpendicular magnetic field. So we compute this term, and then similar to the sum of the previous plots, we take conditional averages of this term over regions where the spectral energy density is high. Okay, so we consider this threshold C, and then we increase the threshold, and when we do this, we actually see that this alignment becomes stronger for more intense structures. So indeed, actually, in structures, there is some dynamic cancellation of this nonlinearity, and this is actually similar to what was found, for instance, in MHD turbulence. So this brings me to my conclusion. So we argue that actually the kinetic scale structures themselves reserve a wave signature, and this is maybe somewhat opposite to one of the present common views in literature, which kind of talks about waves and structures coexistence, so they are kind of mutually exclusive things. And one of the arguments why this might be so is that actually, well, naively speaking, you would think the nonlinear time is accelerated just inversely proportional to the fluctuation amplitude, but actually there's this geometric factor that you have to consider. So actually the structures are not that much more nonlinear, I guess, than maybe anything else that's out there in the turbulence. Thank you.
So we have just about 2 minutes for questions. So
James. What does the kinetic energy spectrum look like when you have this structure? Is it very sharp?
You mean like magnetic energy? Or well, the spectrum is, that's the thing, like when you look at those spectra, like you cannot tell like this is a spectrum with structures or this is a spectrum without, there's no
They look the same.
Yeah, there's no clear, that's the thing. So like you look at this spectra, so you say, okay, this is like a wave turbulence spectrum, so where are the structures? Where are they, So yeah, but in principle, maybe, if they would have some kind of different dynamics of their own, maybe they would also, and if they would carry significant fraction of energy, which a lot of times, if the turbulence is very intermittent, they do, maybe they would modify the spectrum in a total, but it's not quite well. Of course, well, there's in general, like there can be intermittent corrections to the turbulence spectrum. This is actually one very hot topic in kinetic range turbulence. But
is the kurtosis very high? What's the kurtosis?
So this is the kurtosis right down here. So it reaches values of about 6 at the smallest scales, but in the solar wind it's much higher. For instance, here in the bottom, it's about 10, but it's actually, one puzzling thing is that it's constant. So it's the statistics are not normal, but actually not
that high.
Scale dependent.
Great. Yeah. Well, I actually have a brief question too. So this is interesting that you said there's essentially an exact cancellation that enables the nonlinearities to basically vanish, and that's why you can get these kinetic structures themselves having a wave-like nature. But do you think this would persist in a real, say, astrophysical plasma? Because this exact cancellation is because the equations that we write down have certain, geometric properties, which are probably partly because they're idealized equations. I'm just kind of thinking in a realistic astrophysical plasma, you might have essentially sources of noise that destroy the exact cancellation.
Well, I mean, we also compare against measurements of solar wind, so this is one real plasma where we have the best measurements. But
and do you see the persistence of these?
Well, I mean, we get reasonable agreement with this predictions that we kind of out with these simple models. Of course, the agreement is not perfect, but I mean, this is actually a good point. It's by no means obvious that with a simplified model with so many approximations, which are physically motivated, but still there's a large set of approximations, it's not obvious that you would come anywhere close to what happens in a real plasma. Just when we do this fully kinetic 3D simulations in all of their glory, and we check the spacecraft data, we find actually that surprisingly there are some aspects that you can study with this kind of simplified models.
Yeah, I mean, I guess that would make sense if the geometric cancellation is due to some deep symmetry that the real system also has.
That's also true. Like in some kinetic equations, actually, like in some reduced kinetic models, like one model that's often used in this context, like a gyrokinetic model, it's basically like the nonlinearity is like a Poisson bracket, which this linearity is what I showed actually are. So actually, you can have the same kind of cancellation there.
Great.
Yeah.
Well, thank you, Daniel, and let's thank you.
Yeah, so my name is Rohit, and I'm a graduate student at MIT. My advisor is Professor Jan Dunkel. And today I'm going to talk about, as the name suggests, linearly forced flow on a rotating sphere. Maybe I'll stand here. So first of all, thanks a lot for this wonderful conference, and thanks for staying back. I hope that you won't regret this decision after the talk is over. So that's my motivation today. So I'm going to talk about mostly these systems. We have seen videos of beautiful Milky Way galaxy simulations. So this is the best I have. So I'm just rotating my camera a little bit to make it a bit more fancy. But essentially, Jan has already set the stage some time ago about the model that I'm going to talk about. And the broad motivation is really lies with the theme of the conference, which is universality, turbulence across vast scales. So you have these different systems, which are active systems, and people are interested in the dynamics on a sphere. And I'm certainly not claiming anything here, but if you just take a step back, I find it quite inspirational that you can connect these ideas in different systems. So I'm going to talk about the generalized Navier-Stokes equations, which Jan mentioned a while ago. So this is a minimal model that basically talks about an incompressible velocity field. And you have a Navier-Stokes-like momentum equation with some higher order terms that are here. And so these gammas are essentially phenomenological parameters that you put into the system to create an internal forcing through a linear instability. So that's essentially the basic idea. So if you look at the dispersion relation of the system and you flip the sign of gamma 2, so if gamma 2 is less than 0, then you get a dispersion relation that looks like this. And here, what happens is you introduce a band of linearly unstable modes. So you are internally forcing the system so that these modes grow, and these modes which are outside this band basically dissipate. And so what happens is you end up getting these vertical patterns in your flow field, which have a certain dominant length scale, which corresponds to the most unstable wave number. So that is 1 over lambda, which is lambda is the size of your vortices. And there is a time scale which corresponds to the maximum growth rate of that particular mode. There's a third parameter, which is this kappa, which is essentially the bandwidth at which you are forcing. So if this kappa is really large, then that would correspond to sort of forcing at all modes, and it's almost equal to random forcing. And so in the two-dimensional Fourier space, what it looks like is like a racetrack here. So this gray region is where you are sort of pumping in energy, and then the advective nonlinearity carries that energy outside, and the modes get dissipated. So there have been studies of GNS on a non-rotating sphere, where incompressible 2D flow on a sphere was considered using with internal forcing. And I'm going to talk about theta being the co-latitude and not the latitude, and phi is the longitude. And so in the previous paper, Jonas Slomka basically derived the GNS dynamics on a sphere, and he expressed the equations in terms of vorticity omega and stream function psi. And this is just like Navier-Stokes on the left side, and on the right side you have this F that provides an internal driving. So that's really just the key difference that we are adding into this system. And this F is essentially this polynomial with these phenomenological parameters, which are the gammas. Okay. So now what I want to do is take this model and start to consider it as a minimal model by considering rotation. So we want to investigate the interactions of internal driving and rotation. And when you want to do that, you consider the absolute vorticity. You decompose it into a relative vorticity, which is the vorticity in the rotating frame, and the Coriolis parameter, which is 2 omega cos theta. And if you do that, you end up extending these equations with this extra term over here, which has this phi derivative of the stream function. And that's essentially the only difference in the GNS equations in the non-rotating case with the rotating case. And we want to see what happens when we consider this effect. Right? So our equations are these. Again, I want to remind you of this dispersion relation. And essentially, we have 5 parameters. So we have these gammas, we have the rotation, we have the radius of the sphere. And what is actually important is these 3-dimensionless parameters, which I'm going to be using in this talk. Right? So what is important is, firstly, this ratio of r and lambda. So this is how large is my sphere as compared to the size of the vortices that I'm forcing in the GNS model. Then there's the dimensionless bandwidth, which is kappa lambda. And then we have rotation rate, which is as compared to the typical life of these vortices that is again forced by the GNS dynamics. And so we argue that these are the 3 dimensionless parameters that play a role. And we will fix kappa lambda to 1 in this talk. So this time, let's remind ourselves quickly about spherical harmonics. So spherical harmonics are basically eigenfunctions of the Laplace's equation on a sphere. And these are these YLMs, where L represents the wave number in the meridional direction, and phi is basically the wave number in the azimuthal direction. And quickly I want to say that when m is 0, then essentially there's no azimuthal variation, and you have these different L modes that you see on the sphere. Right? So what's interesting, we think, is that this model has stationary exact solutions. And to see how we can construct it, we can again go back to the dispersion relation. And now I'm plotting it in terms of the spherical wave number L. And again, there we have this unstable bandwidth. And at the edges of this, we have this L minus and L plus, which basically make this operator on the right side 0. And it can be shown that they also satisfy the nonlinear operator on the left-hand side. And so spherical harmonics with m equal to 0 with these L's, which lie on the neutral modes of the original dispersion relation, are essentially stationary solutions of this system. So then we go forward and do simulations of the model using Daedalus. So this is, I think, so a few talks I mentioned using Daedalus. And so Keaton Burns, who was originally at MIT, at Flatiron and now is at MIT, helped me set up this code. So let's talk about the simulation. So here, I'm showing you a simulation when omega is 0, so we are not rotating. And as we see this simulation, we can see that there are these vortices that basically are forced. So there's a certain length scale that we can see, and that is forced by the GNS dynamics. And as Jan mentioned earlier, one can actually show that these are the system is basically hopping between stationary solutions for this system when omega is 0. Now, what I'm going to do is I'm going to start to rotate this system at certain rotation rate omega, and then we will see what happens. So here, just visually, we can see that there are these zonal jets that start to arise, and that's predominantly because of the rotation. Another thing that's interesting is that, as expected, the dynamics on the poles is different from the dynamics at other latitudes, equator, where the rotation effects are felt the most. And you can see that there are these persistent vortices that sort of stay at the poles. So what we think is essentially interesting is these zonal jets that arise because of the rotation. And so one can go ahead and think about different R over lambdas in this case, and also different rotation rates. And we can see that as we vary this R over lambda, we can generate patterns of different sizes. And for all these cases, when omega is very large, you have these zonal jets that arise. And what's interesting is they are close to these stationary solutions. So here, these stationary solutions are basically plotted for the L's that we got from these parameters for the dispersion relation. And you can see that the stationary solutions basically capture the bulk characteristics of the solutions at the highest rotation rate. Yeah.
Sorry, what do you mean by zonal jets? Could you point to one?
Right. So the zonal jets are basically. So in the next slide, I'll get to it in the next slide. Yeah. What I basically mean is the velocity is the azimuthal velocity is alternating. That's what I mean by zonal jets.
I mean, are they the little circles that we are seeing on this?
No, they are the bands. Right. So. Yeah. I'm plotting vorticity, but if you plot azimuthal velocity, it would look the same. So I think in the next slide, I have the azimuthal velocity. Yeah. So if you find the azimuthal velocity and the meridional velocity, the azimuthal velocity is what dominates. And so. Exactly. Yeah, that's right. And so, yeah, so we think that the high rotation case is what is interesting. And yeah, maybe I'll go to the next slide first. So here is where there's the vorticity. And then this is the azimuthal velocity, and they sort of sit between the bands, essentially. And so we can think about this from a spectral point of view, right? So here what I'm plotting is the decomposition of this field in terms of spherical harmonics. And the dots are different spherical harmonic modes. The sizes of the dots are the amplitudes, and the color is the phase. And what you can see is that when the system settles onto this statistically stationary state, you see these few modes within the forcing bandwidth that are active, and they correspond to m equal to 0, and that basically sets the length scale of these zonal jets that we see. And so here again, so this is the zonal velocity, and the zonal velocity is alternating, so that's what I mean by zonal jets. And if you look at the total energy, you can see that the total energy basically starts to increase because we are pumping. And then at the end, it settles onto some statistically stationary state where the energy pumping and the energy dissipation balance each other. And what is interesting is that just these few modes, which are essentially active, contribute to most of the energy. And that's what we see at different parameters as well. So you can project the dynamics to these basically few modes and sort of maybe analytically explain what is happening. Right. So the forcing is indeed internal. So there's no external forcing. So that's the sort of the internal forcing that we're talking about. So this F here is what forces the system.
But is it a continuous forcing, or do you put down something initially and then?
Right. So initially we start with a random field. So initially you just start with a random field with a very small amplitude, and then the modes that are in this bandwidth basically start to grow exponentially because there is a linear instability inbuilt in the system. And then those modes, when they grow, they interact through the advective nonlinearity.
And is 500 rotations about the longest length you've run the simulation?
So I have run the simulations for 50 time steps as compared to the activity time scale that we set. So that 500 is actually the rotation rate. And I have, so the time scale that is important is this tau, which is like the vortex growth and decay scale. and we have run simulations up to 50 times that, essentially.
Okay, you might want to try running it. So you can probably do it
Right.
easily. Running it like 2,000 rotation rates.
Okay. Okay.
You might expect the jets to merge with each other.
You might expect what?
You might expect the jets to merge with each other.
I don't think they could.
I don't think they will, because it's really, we are setting the length scale. So if you see this, right? So it's really that there are these modes which will continuously be forced because the forcing bandwidth is right here. What might happen is, because of the inverse cascade, the mode that is sitting right here might start becoming larger, but there'll still be these modes that will be forcing the system.
Yeah, the idea here is the inverse cascade is arrested at the rotational scale, but that arrest mechanism isn't perfect.
Right.
So if you wait a long time, you lose the arrest, and eventually you get energy pileup at low wave numbers.
Right. Okay. Yeah, maybe we can talk about that. But I think you will keep seeing these modes because we have settled on a statistically stationary state. So I think that if you keep running these simulations, it'll stay there, I think. Yeah. Yeah.
Excuse me, does your right-hand side, does it involve negative viscosity?
Yes, it does.
So you have negative viscosity and biharmonic stabilizing viscosity.
Right, that's right.
So you have Kuramoto-Sivashinsky equation in a way.
It's not exactly that. It's a bit different, I think. The structure is similar, but it's not exactly Kuramoto-Sivashinsky.
This is where your instability is coming from. But
right.
Our experience is that if your biharmonic friction is constant, the scheme is unstable. It needs to be flux. I mean,
gives you the instability.
Right. So, and there's also a sixth order. Yeah. So let me go back. Yeah, so here there's the biharmonic, which gives you the instability, but there's also a stabilizing like del to the sixth that basically damps the large wave numbers.
Right, but if your negative destabilizing term is not a function of the flow, then the scheme becomes unstable. You need to make it flow dependent.
It is flow dependent here.
Okay. And if it's flow dependent, then you can extract epsilon. You can actually extract the forcing which goes into the system. I'll show you after.
Okay, yeah. Yeah, so let me just clarify. By flow dependent, what I mean is that this is basically acting on the velocity field itself. That's what I mean by flow dependent. But we can talk about it later.
Is it constant or it's some function?
It is constant, yes. The parameters are constant, yeah. I guess you're mentioning that the parameter should be a function.
Parameter should be.
Okay, maybe we can talk about it later.
Okay.
Yeah. Right. So I have run out of time, but maybe if I can get 2 minutes into the question time, I can talk quickly about these Rossby waves that we see, because I think that's also a very interesting thing. So the westward propagating waves are really Rossby waves that we see, and that's what you should expect. I had a little demonstration for those who are not aware of Rossby waves, but I'll just sort of skip that and just say that we can essentially construct these exact solutions on the sphere as well as on the tangent plane, which is called the beta plane in geophysical fluid dynamics. And again, the idea is similar, which is that you can basically think about these L modes, this L plus and L minus on the sphere, and this K plus and K minus on a tangent plane, because then you can deal with Fourier modes. And have them to be the roots of your polynomial dispersion relation, and then also have these azimuthal modes, which are Rossby waves, so that they have a particular phase speed of these Rossby waves. And so since we have this prediction of Rossby waves, we can just go back in the simulations and try and measure it. So here, what I'm plotting is the deviation of the vorticity from the mean vorticity at different latitudes. And you can see these waves that are going westwards, which are essentially Rossby waves, but we can basically try and measure this phase speed and see if there's it matches with the analytical prediction. And so here, what I'm showing you is the Fourier spectra at every latitude, and you can see that there are these power spectra as a function of latitude, and they sort of tilt. And if we can go back to our dispersion relation, for the Rossby waves, and essentially take into account the fact that we are forcing modes in this racetrack with a minimum k minus and a maximum k plus. What I'm plotting is these white lines with for k minus and k plus. We can see that we can capture pretty much the spread of the power spectra for these Rossby waves. So we think that this model has some usefulness in terms of the analytical prediction capability that one might have. So just to conclude, we have a minimal model for pattern formation on rotating sphere, and we can construct exact time-dependent solutions for zonal jets and Rossby waves, and these exact solutions can be seen in nonlinear simulations. Thank you.
So we have just about 2 minutes for questions, and I'm sure we can use those well, and then any further questions can be addressed during the discussion section which follows. So please, any questions?
Yeah.
So these exact solutions you mentioned, are they nonlinear or are they somehow neutral? I'm not quite clear about that.
So they are.
Does the nonlinear term vanish identically?
The nonlinear term vanishes identically.
And then the linear term vanishes.
Yes.
So they it's not a balance between the linear and nonlinear. It's just.
No, it's not. So it's right. So it's not like a soliton kind of a solution. It's that the nonlinear term vanishes exactly and the linear term also vanishes exactly. And in fact, these solutions are also not stable because of the internal forcing that you have. But we still think they are useful because they give you some idea about the instantaneous nonlinear solutions that you see in the systems. Yeah.
So following up on that interesting question, are you saying that at the level of the differential equation, the nonlinear terms vanish exactly? So is it actually a linear differential equation? And if so, could you then imagine putting in an external forcing and constructing a solution to that forced system with variation of parameters? Like as you might get if you had a little, say, external body like a moon of a planet kind of perturbing the planet.
Right. So, so the equations are indeed nonlinear. It's just that I think the question was, so these exact solutions that we have, are they somehow, if you put in the nonlinear term has some contribution and the linear term has some contribution and they both cancel each other? But I think that's not the case. It's just that for these solutions, the nonlinear term is exactly 0 and the linear term is also exactly 0. But the simulations that we have run, they are nonlinear. So I don't think we can really linearize, if I got your question correctly.
The equation you're solving is still a nonlinear differential.
Yes, it is. It has the nonlinearity of Navier-Stokes, and it just has a linear forcing. Yeah.
Then, so what sets the amplitude of these solutions? Do you have any amplitude you can have?
Yeah, you can have any amplitude you want. Yes. So what we observe in the simulations, I haven't really looked at what sets the, you start at almost 0 energy and you start pumping and the energy grows and then it settles onto a stationary state, right? I don't have intuition as to what sets that final energy length scale, but the exact solutions can have any amplitude. It's just the structure of those equations that we are sort of appealing to. But yeah, that's a good point. I should think more about what sets the final energy in the stationary state.
So the vanishing of the linear, the vanishing of the nonlinear terms is independent of the amplitudes, right? It's just something is orthogonal to something else.
Yes, that's right. Yes, yeah. So that's why we don't have amplitudes for the exact solutions. Yeah.
Can I ask one quick question?
Yeah.
So you have two length scales, right? So you have the radius and then you have this intrinsic length scale.
Yeah.
Can you play with it to? I was thinking you could start to see it in those Rossby wave type things where it looks kind of like a barber pole. You can't quite squeeze things in. I noticed you had a slant on that.
Yeah, that's a So I think that's possible if I make this lambda to be very similar to the radius of the sphere. And so I think Jan showed a movie of the solutions jumping. And so it would be interesting to do that jumping case with rotation, and maybe something like that would. I haven't done that yet, but maybe I'll do that and send you an email. Yeah.
Okay, well, maybe we should move to discussion. So James, if you'd like to take over the sharing responsibilities, let's think.
All right, thank you.
Thank you. Everybody can hear me okay? Yeah, so I've listed some questions that came up during the session, which seems to be coming up actually repeatedly all throughout the workshop. These are just few ones. We can talk about this, but we can also, if you have more questions from the session, we can start off with that. So it's your choice. Because it's like giving a lecture. Nobody wants to talk. Did we? Okay. Okay. What about the?
Maybe the answers you received you felt were unsatisfying.
No, I don't have any preconceptions or any pre-notions. Why don't we start with the first one? And if you feel like we discussed the second one, we can jump to the third one. So the first one's this problem that Ethan mentioned several times, but perhaps not wanting to mention it directly, is this critical challenge for numerical models. And I think I sum it up basically as the problem of properly resolving the flow. This has been a critical problem ever since we started solving Navier-Stokes numerically. So, question that I want to pose to the audience, that the two people that are left, can anything be done about this problem? See, we gotta.
I mean,
can
anything be done? I mean, I don't know, quantum computers, but like in lieu of that, actually, one thing I haven't seen too much, although I'm sure it's in the papers, is resolution studies, and they're extremely important. So, like for example, Shmuel Bialy, who presented on Tuesday but isn't here, we're working on looking at some different types of turbulence statistics where we change the driving scale. And of course, the boxes are already so small that if we try to push the driving scale a little lower, we have to do a lot of convergence tests to make sure whatever statistic we're looking at is, properly converged. So I think in terms of point number one, the main thing we all need to constantly be doing is to be doing convergence studies to make sure what we're looking at is actually, physical and not just numerical.
That's right, and I would add to that you need to do these convergence tests for every problem, different problem you're doing. There's no universality to the convergence. Yeah.
Happy to continue on the same point. Also, better algorithms is something that we definitely need. In particular, in compressible turbulence, when we start modeling it using supercomputers, we use second-order accurate schemes, which is not good for turbulence. So we really need to concentrate on development of stable high-order methods for compressible flow. And so funding should go in that direction, I think, if you want to learn more about it. My experiments with this, so I was showing some results from seventh order accurate in space at low Mach numbers. There are very efficient algorithms. The issue is their stability, of course. But for example, if you use nonlinear filter scheme of seventh order, it is 15 times cheaper than standard VIN of 5 computationally, if you want to recover the scale separation that you need. So I think definitely the future is in that direction. But I'm not sure there is enough effort in the community.
CCM?
Yeah, I mean, I'm just when you say stable higher order schemes for compressible things, I'm assuming you mean for shocks in particular.
Yes, absolutely. So in the incompressible world, we have kind of spectral methods as standard, but unfortunately, when compressibility and shocks show up, it's very hard to get the same quality of solution unless you go to high order finite difference or finite volume methods. And I think it's a necessary step, because otherwise we are wasting cycles of our computers for nothing.
Well, you get same quality of crappiness, right?
Right.
This note of the computational side, I was a little surprised no one mentioned GPUs, because I think that's something that has really become more accessible in the last few years and more possible to code for. And my understanding is GPUs do very well when you have a high flop to byte ratio. So essentially when you're doing a lot of computations on a small amount of data, or when you have a problem that parallelizes really well. And I just kind of wondered, have people in the community been thinking about algorithms for turbulence studies that are well suited to GPUs, and or the impact GPUs can make on this?
Do you want to say something about it, or? Okay.
I know there's a group at MSU. There's a group of people at MSU that are using GPU to look at turbulence, MHD turbulence. They're actually his name is Philip, right? Yeah, yeah. He actually developed, or he sort of wrote a wrapper so that you can basically transform a C++, yeah, to a GPU compatible code. So just take a normal code and then it becomes GPU compatible. And yeah, you're right. Yeah, people are doing that.
I mean, but that's true in certain types of applications. You can get a big speed up out of GPUs, but it doesn't cure the problem that lots of schemes are not well suited to the problems that they're purporting to solve, right? I mean, resolution, yeah.
Do people have feelings about finite difference or finite volume versus spectral or some other algorithm? Yes.
I have feelings, and as a non-numericist, I feel.
Can you please use your C mic?
Oh, right. Excuse me. I have passionate feelings, despite the fact that I'm not a numericist.
But that's fine.
Spectral methods are wonderful in MHD because they give you sufficient accuracy and reach that you can do much more realistic computations. I think that's generically true in turbulence, where there's this enormous difficulty that we have in getting adequate resolution. But it's really hard to combine spectral codes with any kind of realistic background environment. Mm-hmm. And I don't know what the solution is supposed to be.
There are algorithms such as spectral element methods that's sort of combining spectral algorithm locally, but it's on a grid. So, but I guess for most of us doing physics work, we don't generally tend to worry about funny boundaries or funny shaped boundaries or so forth. But
these things arise spontaneously in some environments. Yeah. And even if it's not funny shaped, if you're doing like an accretion disk, you have this problem that, or a star, you have this problem that there's a set background with a broad range of scales against which you're trying to calculate convective turbulence or, magnetic field generation.
For the spectral methods, is it just the usual that if you have Fourier modes on a funny boundary, you
just basically Fourier modes on background.
It's hard to find a basis for.
Yeah. The whole point with spectral methods is that you have spectral convergence, but that's only in the presence of smooth things.
Right.
And so if you have shocks and that kind of stuff, then all that is out the window, and you devolve to some sort of first or second order scheme, just because your Fourier modes are now decaying so slowly.
What about? The advantage of the spectral methods is the Fourier modes are eigenfunctions, so you get algebra equations. But that's not just true of Fourier modes. You could imagine compactly supported analogs like wavelets having nice properties and using those. Okay.
Yeah, yeah. I personally also use a method called contour dynamics, developed by contour dynamics. Yes. So originally developed by Norman Zabriskie, based on actually nuclear bag models, right? And for certain types of problems, namely 2D non-divergent or quasi 2D type problems where the vorticity has an inversion, which allows you to obtain the stream function from it. It's fantastic. It's actually even, I think, much better than spectral methods. But the problem is, it's only really good for the situation where there's inversion is possible. When it's not possible, it doesn't mean you can't use it, but it's, again, then it's the same as spectral or finite difference method.
Can you know a priori the vorticity will be invertible throughout the problem? Like if there's some theorem that it's invertible?
Yeah, because that's a conserved quantity. So if vorticity is conserved, then it's invertible. Of course, its strength is it in some ways its worst enemy because it's an inherently an inviscid algorithm, so that if you're trying to do very complex, if you're trying to model a very complex flow, the complexity of the flow just overtakes, it exponentially increases, so you just quickly run out of memory. So the way around that was to implement something called surgery. There are various different forms of surgery, but essentially what you're trying to do is if vorticity contours are conserved for topological reasons, you can disconnect the vorticity lines if the scale, if it develops kinks or small scales that perhaps doesn't really do too much to the flow, and you can disconnect and smooth that contour out and reconnect, right? So that's one way of getting around it. And it's ad hoc, but the power of doing that comes from the fact that you tend to smooth along the contours rather than across, which all the other algorithms do. So if you have a jump, for example, like a shock-like structure, you can retain that all the way throughout the calculation without loss, essentially. Any other comments, feelings? We have just 1 minute and a half. Do people they want to talk about the third item, or you're already ready for coffee? This came from actually Boris's talking with Boris this afternoon. Yes. So speaking of the devil.
Was here.
Yes, devil. Please speak.
When you talk about Kolmogorov scaling, I was talking about anisotropic scaling as well. So I was saying that in some flows you can have this steep spectrum which is not determined by Kolmogorov cascades, but in other direction it's still going like Kolmogorov. So the fluxes are still important. They're just not important in general structure of the spectrum because it creates structures along the directions when you have steep spectra. Okay, so you cannot really say that Kolmogorov is becoming secondary when you have extra strains. It's just becoming much more complicated. And even the last talk which we had, simulations in the sphere, if Rahit computed spectrum in two directions, like zonal and residual spectrum, non-zonal, he would have seen that under strong rotation, zonal goes like beta square n to minus 5, whatever beta it is. But in residual direction, it's still Kolmogorov spectrum. It goes like minus 5/3. So, and the fluxes are going by this. So I think we need to be careful when we deal with anisotropic spectrum.
But you also mentioned that for a broad range of two-point correlation function, it always leads to a minus 5/3 type spectrum.
It's for some.
So there's no physics in this, and yet it
there is a physics. Actually, I told you Kolmogorov wrote another paper before this Kolmogorov 41. There was Kolmogorov 37 in German, in which he goes into a random walk theory, and later on, just several years ago, quite an old Russian academician who worked with Kolmogorov, believe it or not, Georgy Golitsyn, he says that
Golitsyn, right?
Golitsyn, yes, the conditions set up by Kolmogorov so general that Golitsyn says they describe most of the phenomena in the universe beyond fluid dynamics. So, if we explore this, we probably will find some interesting things. So don't be surprised that Kolmogorov spectrum works so well. You just need to have certain correlation function for the phenomena you consider, which is delta decorrelated in time. All right. So I think that it may explain at least partially why Kolmogorov spectrum is so well observed.
What do you mean by delta decorrelated in time for those of us?
Well, it has a structure delta t minus t prime.
So it's basically you only have equal time correlations. Is that right?
Yeah, wide in time.
It's a white noise.
White noise in time.
Yeah.
In time, yes.
You think did you
comment that it's not all that good, because when you have some dissipative channel available, as you do in supersonic turbulence,
right,
or if there's resistivity larger than viscosity, you can get a -2 power law, for example.
Right.
And I think generically one can say that putting some dissipative channel into turbulence will bring you away from Kolmogorov.
Also, if the flow contain high amplitude or finite amplitude waves, for example, that also is a situation where it doesn't work so well.
No. For this, I'll tell you something else. You need to consider it's one-dimensional spectrum or three-dimensional, because oftentimes we integrate over the wave number, and then you smear the peculiarities of the one-dimensional spectrum. If you have one slope in one direction and one slope in another direction, when you integrate it, what slope do you get? In addition, you have intermittency effects. And in addition to this, you may have waves. And waves also add to the spectrum, and they also produce their own intermittency. Mm-hmm. It looks like intermittency, but it is not intermittency, it's waves. So it all need to be carefully considered to judge the slope of the spectrum. And what I'm telling you is that slope is not even as important as amplitude. The physics is not in the slope, the physics is in the amplitude.
Okay, I think we went over time, so maybe this is a good stopping point. And I'd like to thank the speakers from this afternoon and also the audience.